Absolute value is the distance a number is away from 0 on a number line. For example, if we want to illustrate the absolute value of -5, we can write our number line, we have 0, and then we have -5. And we can see that -5 is just 5 away from 0. Because there is no such thing as negative distance, the absolute value of a number will simply be the positive version of that number. When you're solving an equation with absolute value, you can simply take whatever is inside the absolute value bars and change that to the positive number. So in this case, I could rewrite the equation as positive 3 plus 2. So my answer is obviously 5. When you have a mathematical operation inside absolute value bars, you want to do the math inside the absolute value bars before you let the absolute value bars take away any negative signs. So in this case, we would add -3 to positive 2, and we would rewrite the equation as -1 with the absolute value bars around the -1. Then the absolute value bars take away the negative, so we rewrite the equation as simply 1. When you have a variable, such as x or y, inside absolute value bars, you really can't tell whether the absolute value has taken away a negative. Meaning, if I said to you the absolute value of x was equal to 5, you don't know if x is equal to 5 or if x is equal to -5, because both the absolute value of 5 and the absolute value of -5 both equal 5. As such, when you have a variable inside absolute value bars, you have to rewrite that equation into two separate equations. So in this case, if we say x is equal to the absolute value of y, you need to rewrite that as either x is equal to y or x is equal to -y. When you're dealing with inequalities, the same ambiguity about what's inside absolute value bars still exists. For example, in this case, we don't know if z minus 5 is positive or negative. If z minus 5 is positive, then the absolute value bars really haven't done anything to the expression. So we could rewrite that as x is greater than z minus 5. However, if z minus 5 is negative, then the absolute value bars actually gave us the negative version of z minus 5. So we would have to say that x is greater than negative parentheses z minus 5. Here's a fairly standard absolute value data sufficiency question. We're being asked to find out what is the absolute value of x. If we first take a look at statement 1, we see we have a variable inside the absolute value bars. That means we're going to have to write two versions of that equation, one positive and one negative. So my first equation is x plus 3 is equal to 4. Or I could also write x plus 3 is equal to -4. Then I'm just going to solve each equation individually. On the top equation, I subtract 3 from both sides, and I get x is equal to 1. On the second equation, I do the same thing, subtract 3 from both sides, but this time I get x is equal to -7. So because I have two separate answers for x, there's no way I can definitively tell you what is the absolute value of x. For statement 2, there are really two ways that I could approach the information they give us. The easy way would be to simply subtract 3 from both sides, and I'm left with the equation that the absolute value of x is equal to 1. And that would obviously answer my question. Or I could follow steps I followed in statement 1 and break what's in the absolute value bars into a positive and negative. So I get two separate equations. So statement 2 could break down to x plus 3 is equal to 4, or negative x plus 3 is equal to 4. And then I just solve each equation individually. Subtract 3 from both sides, and I get x is equal to 1. On the bottom equation, subtract 3 from both sides, and I get negative x is equal to 1, or x is equal to -1. But remember, they're not asking for what is the value of x. They want to know what is the absolute value of x. So if I have 1 or -1, when I put absolute values around those numbers, I get the exact same number. They both equal +1. So either way you look at it, statement 2 is enough, but statement 1 is not.